Hello, this is a video on how to prove triangles congruent. If we take a look at our textbook, Chapter 2 talks about the rigid transformations, which of course are the translations, rotations, and reflections. And then Chapter 3 defines congruence using the transformations. In fact, Section 3.1 defines congruence using the rigid transformations. When a figure is transformed with one or more rigid transformations, an image is created that is congruent to the original figure. We saw this previously. In other words, two figures are congruent if a sequence of rigid motions will carry the first figure to the second figure. And I have that first definition up here. An alternate definition states that two polygons are congruent if and only if all of the corresponding sides are congruent and all of the corresponding angles are congruent. So if we come back to Chapter 3, we looked at the definition of congruence, and this definition is using transformations. And we now go to Section 3.2. And I'm going to scroll past this first little question. It's a little bit off the wall, and come right down here to ASA and AAS triangle congruence. Here's the idea. If two triangles are congruent, it means that all the corresponding angle pairs and all the corresponding sides are congruent. However, in order to be sure that two triangles are congruent, you do not necessarily need to know that all the angle pairs and all the sides would be congruent. That would be showing 6 things, and it is not necessary to show 6 things congruent. If you have kind of a correct three pieces of information will be enough. So let's take a look at our first congruence theorem. In this particular figure, we have a 51-degree angle, a 45-degree angle, and contained between those two angles is a length of 7. In the other triangle, we also have 51 degrees and 45 degrees with the segment between the given angles as 7. This is an example of angle-side angle. Let's read the ASA criterion. The ASA criterion for triangle congruence states that if two triangles have two pairs of congruent angles and the common side of the angles in one triangle congruent to the corresponding side in the other triangle, then the triangles are congruent. Yes, it looks like I can rotate it there, and we see the triangles are congruent. So here is the angle-angle-side criterion. The reason this works is because if you have two angles congruent to two angles, the third angle has to be congruent because the three angles add up to 180, and then you're back to angle-side angle. So rather than having to prove that every time, we make the AAS theorem for convenience. There are going to be 5 ways to prove triangles congruent. Here in 3.3, they talk about side angle side. This is, of course, two sides with an included angle between those sides. side, side, side with no angles needed. And then the last one is a special case that applies to right triangles. It's called hypotenuse leg, and I think it's in this section here. Let me see if I can find it. Yes, here it is. This only applies to right triangles. Anytime you have the hypotenuse congruent and one pair of legs congruent, the hypotenuse is congruent and one pair of legs congruent in two right triangles, then the triangles are congruent. Okay, now let's go over to the week 6 examples and try to write some proofs. The first one we pretty well have started, but it's a good starter. I have what I'm trying to prove here is triangle EFG is congruent to triangle EHG. The given information is that segment FG, this one down here, is congruent to segment GH, and those are marked with a single mark. The second piece of given information is that segment EH is congruent to segment EF, and these are marked with 2 marks. The only thing we need to do to complete this is to have segment EG congruent to itself. This is a 2-column proof. We do want to state the givens. Here's my first piece of given information. Here's my second piece of given information, and the reason is that that was given. Segment EG is congruent to segment EG. That's a reflexive property of congruence. And then our conclusion, which is also our last line of our proof, is that triangle EFG is congruent to triangle EHG. And the reason for this is side, side, side. And I can just put SSS here. And that completes my proof. Now let's take a look at example 2. The given information is that segment PM is perpendicular to segment LN. So I have a right angle there and I have a right angle here. The other piece of given information is that I have angle L congruent to angle N. I will comment that angles and segments can be congruent, which is different than being equal. Equal things need to be numbers. So if we talked about the measure of angle L, that would be equal to the measure of angle N. Numbers can be equal. Geometric objects can be congruent. Unfortunately, I may not be able to keep these annotations on my screen because I still don't have my pen mastered. So please record these markings. Now, I do want to prove the triangle LMP is congruent to triangle NMP. Please notice that these are written in corresponding order. It'll be important for you to do that also on your proofs. Now, so far we only have 2 pieces of given information. We need something like side angle side or side side side, etc. But we do have a common side here. So this side is congruent to itself, and this is going to allow me to use angle-angle-side. So we have our plan for our proof. Now let's see if we can write up our proof. Okay, I have my 2 columns. The left-hand column are going to be the statements, and the right-hand column is going to be the corresponding reasons. If you'd like, you can put all of the given information in one statement. The reason is given. Statement 2 is going to be that segment PM is congruent to segment PM. And the reason for this is reflexive property of congruence. I do have a side congruent. I do have an angle congruent, but I do not have the other pair of angles congruent. We can't just assume that those are congruent. We need to prove that they're congruent. So these angles right down here are right angles because of the definition of perpendicular. So my next statement will be about the right angles. I'll go ahead and write that in now. Angle LMP and angle NMP are right angles, and the reason for this is definition of perpendicular lines. Now that they're right angles, we can state that they're congruent using the theorem that all right angles are congruent. So we have angle LMP is congruent to angle NMP because all right angles are congruent. And now I have enough information to make our conclusion. And my reason over here is angle-angle-side. When we're using angle-angle-side, we need to make sure that we have angles congruent in two different places and sides congruent, and the side would not be included between the angles. Now let's move to example 3. Let's see what we have here. Segment VW is parallel to segment YZ. We often indicate parallel lines with an arrow. We also have segment VW congruent to segment YZ. So not only are they parallel, they're also congruent. And we're trying to prove these two triangles are congruent triangles. Well, if we take a look at our parallel lines, this angle here at W is congruent to this angle at Y because they're alternate interior angles. You might need to turn your paper a little bit to see that. This angle at V is going to be congruent to this angle at Z for the same reason, alternate interior angles. Notice that I have not marked angle V with a single mark because angle V would not be congruent necessarily to angle W and angle Y. The angles at X actually are congruent as well because they're vertical angles, but I have enough information to do an angle side angle proof. Once again, I may be losing my annotations, so please have those on your paper so that you can refer to them. And I'm going to get ready to write the proof. So now we have stated our given. It's usually a good idea to get the given information written in your proof right away. Now we're going to state the angles that are congruent. Angle W is congruent to angle Y. So we have angle W congruent to angle Y. When there's only one angle at a particular vertex, you do not have to write all three letters. The other pair of congruent angles are angles V and Z. And this is by alternate interior angles. This is by alternate interior angles. This is not the full theorem, but we will be a little bit lenient on this and say that it's okay to state alternate interior angles. So let's take a look and see if we have enough to make our conclusion. I believe we do. Here's angle, and here's the side that is contained between the angles, so I can make my conclusion. And my conclusion has a reason of angle, side, angle. Okay, now there are quite a few little subtleties and quite a few questions that are going to come up in the proofwriting process. Rome was not built in a day, so please ask your questions at the Zoom exchange. Either of the Wednesdays that will be available before this assignment is due. If you'd like to call me on the phone or send me a draft of a particular proof, I'd be happy to look at that. Just in closing, there might be someone that would think that, oh, well, I don't think I'm going to have to teach proofwriting in middle school or junior high, and so therefore I shouldn't have to learn this. That's never a good approach. In general, I'm teaching this for a number of reasons, and I won't give the 35-minute lecture why this is a useful thing to learn. But there is a possibility that you would teach it, but probably also important is that if you look at the framework for the content test for middle school mathematics in Illinois, you are expected to be able to analyze proofs. And it's very wonderful mathematical thinking. Have a great day.